Wait. Good morning, everyone. Myself, Aachal Rajesh Vaidya, and my roll number is 2101. Today, I am going to present an ISE presentation on topic bending stresses in aircraft wing spars under aerodynamic lift load. So, this is a topic from solid mechanics. As a part of ISE, I have to present a presentation. So, let's start with the introduction. So, the aircraft wing supports the lift force generated during flight, the basic information we know about aircraft wings. Now, the wing spars act as the main structural element carrying bending loads. As you can see in the diagram, the wing spars are the main component or structural element which carry bending loads. Now, why bending stress arises? It is due to the distribution of lift along the spans, as we can see in the diagram. Okay. Now coming back to the topic, the wing structure overview. Okay, so before talking about the wing structure, we must know the main component of wing structure. So there are four main components of wing structure. First one is spars, second is ribs, third is stringers, and fourth is skin. So here in diagram we can see ribs, spars. There are two types of spars: rear spars, front spars, and nose ribs, normal ribs, stringers, skin. Here it is also ribs. So let's talk about spars. Spars run span-wise. They resist bending and shear loads, typically made of aluminum alloy or composite. Now, talking about bending moment distribution. We know each span-wise section must carry lift from the outer portion of the wing. And let's calculate bending moment at a random distance y. So to calculate bending moment, we know like the maximum bending stress occurs at wing root. So we will take a random distance y. For that, we will calculate bending moment. And m of y is equals to integration of y to the limit b by 2 L of x minus y dx. Here in diagram, you can see bending moment, the direction, and force distribution within the beam. Okay. Now talk about the aerodynamic lift distribution. So we all know that lift is not uniform. It is higher near the root and lower near the tip, approximately as elliptical lift distribution. Both are almost same, but here the total lift generated is equal to the weight of the aircraft in level flight. So the equation is given by L of y is equals to L max root of 1 minus y by b by 2 whole square, where y is nothing but span-wise portion or b stands for wingspan. Let's take a simple example to calculate the maximum bending stress, moment of inertia, and shear stress. So, taking span is equals to 10 meter and lift is equals to 5000 Newton per meter uniform. Cross section rectangular 100 mm into 200 mm. We will find first maximum bending stress and it occurs at root, I already mentioned. So let's calculate maximum bending stress, which is denoted by WL square by 2, where W is equals to 5000, L is equals to 10. After calculating all the calculation, we get maximum bending stress at root is equals to 2,50,000 Newton per mm square. Let's calculate moment of inertia. For rectangular section, the moment of inertia is calculated by bh cube by 12, where b is nothing but 0.1 and height is 0.2. Here in cross section we can see this. So the final answer we get is 6.67 into 10 to the power minus 5 m raised to 4. Now let's calculate shear stress. Nothing but maximum shear stress, which is nothing but maximum bending stress upon moment of inertia. We got this as 375 megapascal. Okay. Now let's talk about spars in a beam. The spars can be moduled as a cantilever beam fixed at the root. Lifts act as a distributed load along the beam. And bending stress at any section is denoted by sigma is equal to m of y c by I. We already see in this calculation where m of y is nothing but bending moment, c is distance from neutral axis, and I is equal to second moment of area or moment of inertia. Okay, so let's talk about the end, which is nothing but conclusion. What we get from here it is, from this PPT, we got to know that aircraft wings parts plays a crucial role in carrying the aerodynamic lift loads under acting on the wing, and the uneven lift distribution along the spans create bending moments, which is higher at the wing root and decreases towards the tips, which results in bending stress, compression on the upper side, and tension on the lower side. Accurate predictions of this stress is essential for safe and efficient design, ensuring the spans can withstand maximum load without failure or extensive deflections. Material section, cross-sectional geometry, and structural optimization helps achieve a balance between strength, stiffness, and weight. This three plays a major role in aircraft structure. Modern aircraft design increasingly use composite material so they can reduce the weight and maintaining high bending stress and fatigue resistance. This is all. Thank you. ए सना हुआ मीटिंग एंड करो सीधा स्टॉप शेयरिंग नहीं करो क्या कहाँ होता है नहीं दिख रहा है ले पकड़ उसको एडिट कर उसको यूट्यूब पे डाल आगे का क्रॉप करके पीछे का क्रॉप करके बस ना कर बाय ये पकड़ तेरा लैपटॉप उठ जल्दी अब मुझे जाने पे कितनी सेल्फी